Alright, let's get started. First, all reference equations and tables will be found from textbook Fundamentals of Engineering Thermodynamics, 7th edition by Morin and Shapiro. Start with problem point 128. Air as an ideal gas with K equals 1.4 enters a converging diverging nozzle operating at steady state and expands isentropically as shown in figure P9.128. Using data from the figure and from table 9.2 as needed, determine A, the stagnation pressure in pounds per inch squared and the stagnation temperature in degree Rankine, the throat area in inches per squared, and the exit area in inches squared. Now let's first draw and write out all given information for air as an ideal gas. And as you can see here, I've already done that. We know that our Mach number at state 1 is 0.2. Our mass flow rate is 1 pound per second. Our initial pressure is 77.8 pounds per inch squared. And our initial temperature is 595 degrees Rankine. Now from table 9.2, we know with a Mach number of 0.2 that T divided by T naught equals 0.99206 and P divided by P naught equals 0.9725. Now I'll show you the table where you can find those numbers. Here's table 9.2, isentropic flow functions for an ideal gas with K equals 1.4. Now you can see the above equations, T divided by T naught, P divided by P naught, and A divided by A asterisk. Those equations will become in handy as our following Mach numbers of 0.2, 1, and 1.5. Here you can see the given values and all the numbers that you'll need. Now having your values, let's scroll back to our initial problem. And to find the stagnation temperature and the stagnation pressure, as you can see, I've already solved it out, so I'll walk you through as you're solving your equation. T divided by T naught is equal to 0.99206 with a Mach number of 0.2. So as you work across your problem, you'll find that T naught is equal to 599.8 degrees Rankine. The same scenario with your pressures. P divided by P naught equals 0.9725. As you multiply across and plug in your initial values, you get that the stagnation pressure is 80 pound-force per inch squared. Now to find the area of the throat, we will need to know its temperature, pressure, specific volume, and velocity. All values denoted with asterisks pertain to the throat. First, we'll use table 9.2 to find temperature and pressure as we did with the stagnation values. So you can actually go back, and it's to note that at the throat, we are assuming that the Mach number is equal to 1. As we scroll back to our problem, you can go ahead and go down. As with our stagnation temperatures, we will find the throat temperature and throat pressure with the same equations, just different values from table 9.2. As you can see, T asterisk divided by T naught equals 0.83333. T naught being the value that you found initially as the stagnation temperature. When you multiply across, you get that T asterisk is equal to 499.83 degrees Rankine. This is the throat temperature. As with the pressure, P asterisk divided by P naught equals 0.52828. As you multiply across with your given value of your stagnation pressure, you get that the throat pressure is equal to 42.3 pound-force per inch squared. Now, as we said before, we are going to find the specific volume. In our case, we are going to use equation 3.34. As you can see here, we have already solved out the equation with our given variables, and I'll walk you through it as you solve it yourself. As again, all asterisks pertain to the throat. So we have PV equals to RT. As you multiply across, you will get V asterisk equal to 4.376 cubic feet per pound. And as to finding the velocity at the throat, we use equation 9.37, where that will be V equals the square root of kRt times the gravity component. As you multiply across, you'll see that the velocity at the throat is 1096.21 feet per second. Now, due to knowing the mass flow rate, we can use equation 4.4b to help us solve for the area of the throat. As we scroll down, you'll see that I've already solved the problem, and we plug in our initial values and do a little bit of math. So you see that 1 pound per second times 4.376 cubic feet per pound divided by 1096.21 feet per second is equal to the area of the throat, which is 0.003992 square foot, which is approximately 0.576 inches squared. Finally, we can solve for the area of the outlet from table 9.2, knowing Mach number is equal to 1.5. As you can see below, A2 divided by A asterisk is equal to 1.1762. Plugging in the values that we found for the area of the throat, you get 0.575 times 1.1762 is equal to the area of the throat is equal to 0.676 inches squared. Now to review the equations. Number 1, T divided by T naught equals value of table 9.2. Number 2, P divided by P naught equals value of table 9.2. Number 3, PV equals RT, equation 3.34. Number 4, C equals the square root of K times R times T, equation 9.37. Number 5, M dot equals AV divided by specific volume, equation 4.4b. Number 6, A divided by A asterisk equals value of table 9.2. Now to review the final answers to your initial problem. A, T naught equals 599.8 degrees Rankine, which is the stagnation temperature. P naught equals 80 pound-force per inch squared, which is the stagnation pressure. B, A asterisk equals 0.575 inches squared, which is the area of the throat. And C, A2 equals 0.676 inches squared, which is the outlet area.